All right, so this is 4.6, Foundations of Math 30, 4.6, and we are talking about combinations, of course. And for number 4, it's pretty basic, just evaluate the following. So obviously you do have a NCR button on your calculator, which I encourage you to use. However, you will need to still show that you know what the formula looks like. So the NCR formula, remember, is n factorial on top, and it's the same as the permutation formula, right? Which this is the permutation formula, but we have to further divide by r factorial. So please remember that as well, and I will show you the long way for this one. So the total n is 5. We have 5 things here that we're choosing from, and we need to choose 3 of them at a time. So we're going to do 5 minus 3 in here, factorial, and then we're also going to divide by 3 factorial. So if you're showing your work here, you could just pump this into your calculator, it's no problem. This really is 5 factorial over 3 factorial times 2 factorial, right? Or you could realize this as 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial. You can then see that the 3 factorial goes away, and you have 5 times 4 is 20 over 2 times 1 is 2. So this should be 10. Do you get that for an answer? For A? For A? Everybody got 10 there? Okay. We could confirm that with our calculator, and of course we'll do that. So let's turn our calculators on, and we've done a few of those already. So I'm going to go 5. Oh, I don't have 5 choose 3. I have 5 choose a lot of things, but. And in here, for me, it's math, back to probability. There's number 3 is NCR. So 5 choose 3 is 10. Oh, good. We did that right. All right. Remember this notation, the 6 over the 4. That's just another notation for combinations. So that's going to be 6 choose 4, and we'll do the same sort of thing that we did with A. 6 choose 4 this time. And so that's 6 factorial over 4 is r, so 4 factorial. 6 minus 4 is 2 factorial. Okay, that's 6 times 5 times 4 factorial over 4 factorial times 2 factorial. Those are gone. That's 30 over 2 is 15. That's what I get. But let's double check that. So 6 math back NCR choose 4 is, 15. Good. Got that. Okay. Another one of interest might be 10 choose 0. Okay. If you have 10 items and you're planning to find groups of 0 of them at a time, how many ways can you do that? If you're choosing one thing, you can choose one thing out of 10 times. But if you're choosing 0 things, and if 0 is an actual number, and if choosing 0 is an actual action that you can do, how many different ways can you do that? Well, let's use the formula and find out. It's 10 factorial over 10 minus 0 factorial, also divided by 0 factorial. So this is 10 factorial over 10 factorial times 0 factorial. If you guys remember, 0 factorial is actually equal to 1. And 10 factorial divided by 10 factorial is also equal to 1. So there is one way that you can actively choose 0 out of 10. You can actively choose 0 out of any number of items, only once. So that's always 1. Okay? Anything choose 0, 1. Okay? 0 choose 0, I suppose that would be 1 as well. If you have nothing and choose nothing, there's only one way you can do that, I guess. You might think that's infinity, but I don't know. That will work out to 1 as well, it looks like. Okay, any problems with 4? We're good? 4 is pretty basic? Okay. 8. Anybody have trouble with 8? Yes, I see one nod. Okay. Let's take a look at this. It seems confusing maybe at first, but let's see what it looks like. Connie's softball team has 15 players. How many ways can the coach choose his starting lineup of 9 players if Connie must be the pitcher? All right, so here's the catcher. Here's Connie. Here's first base, second base, third base. Here's left field, center field, and right field. Okay, so that's sort of how we set up a ball team maybe. And Connie has to be pitcher, so she is effectively taken out of the group, already set aside for the pitcher. Okay, so there's only one way that Connie that the pitcher can be chosen, and that's one player, Connie.
I hate to be a nang, but there are 7 players, and you forgot shortstop.
1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry. 7. What did
you forgot shortstop?
Yeah, I did forget shortstop. Thank you very much. Shortstop is right there. I'm not sure what you said about the 7 players. I guess I had 8, right? Didn't I? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you're right. Thank you, shortstop. I got ahead of myself. Shortstop is right there. I'm doing the bases instead of the positions. That's what messed me up. So second base really should be there, playing there. Okay, thank you. That is, yes, I did play ball growing up. My mistake. All right, so one choice for pitcher, and namely Connie. So that's 1 there. Now the rest of the team, which is now 14 players, there are 8 positions, okay, 8 positions left. So 1 times, this should be 14, choose 8. And again, if we're not considering positions like the shortstop, which I forgot, if we're not considering who's playing where, or that's not a big deal, you just choose 8 players for the remaining positions. That would be a combination type, okay? If it's important who plays what, that's a different question. All right, so that would be the explanation for A. Combinations would be you're just choosing 8 players to fill the positions. There's no condition that has to be met for any of the other positions. It's just 8 random players. Go out there, fill a spot. Yep.
For this question, what I did is 15C10.
Okay.
I don't know if that's correct.
You did 15C10?
Yeah, I got the same answer. I
Mm.
don't know if it's correct.
Yeah, that might, okay, so yeah, 15, choose 10, boy, I don't know. No. There are other combinations, like, yeah, I know 14 choose 1 and 14 choose 14, they would be equal. 14 choose 2, 14 choose, So if you, those would be equal numbers. So I think that's just, I wasn't prepared for that question, but I think that's just a coincidence that you got the right answer. So 10 players, we wouldn't have 10 spots at all, and the choosing of Connie for the pitcher wouldn't add another spot per se. So actually, yeah, I think it should be taken away. Now, we can double check that. Is 14 choose 10 the same number as 14 choose 8? It might be, so you might have accidentally got the correct answer. Congratulations for that. But let's just see, okay? We'll use our calculator here. And I do want to check the other one as well, of course. 14 choose 8 is 3,003. You guys get that? So 1 times 3,003 is 3,003 different ways. Now, just out of curiosity, 14... Oh, you did 15. Oh, you did 15. Oh, okay, interesting. 15, yeah, 15 choose, we just randomly threw another player in there. 15 choose 10 is 3,003 as well. Yeah, okay, so coincidentally, that's the same answer, but I'm not sure you could rationalize that, okay? So it would have to be probably this other way. But yeah, there are different combinations of N's and R's that could yield you the same number of combinations, for sure. Yes? Okay, good question. Would you get this right on a test if you did it that way? Okay, so the reason why we show our work is that so that I can give you marks for your correct process. So if you have an incorrect process, but coincidentally, let's say do 2 things wrong that end up, counteracting each other, that you accidentally get the right answer, you would get most marks for the question, but you would definitely not get full marks, okay? All right, if I was told to do something and I did the opposite but ended up getting the same result, you wouldn't get full credit for that process. So yeah, so if you did 15 choose 10 and accidentally, and got coincidentally the same number, you wouldn't get full marks for that. Yeah. Just like if you said 2 times 1 was 3, and then somewhere else you said, 4 minus 1 was 2, and they counteracted each other somehow and you got the right answer. That's why we show our work. That's why I'm able to give you full marks for complete process. So good question. The answer, unfortunately, is no. But if it was a small mistake, I would take a small amount of marks away. This one, if you did 15 choose 10, for some reason, there would be no connection to 15, no connection to 10. So you'd probably lose a little bit more marks than if you just accidentally, inadvertently wrote down the wrong number. Do you know what I mean? So that's part of the teacher's job, is to kind of assess how much of the full process and the full understanding do you have, which, yeah, is not easy sometimes. But okay, let's quickly just do a little bit of 14. Then we had a question about 17 as well. So let's do a little bit of 14. I did have a question about this because it looks a little confusing. Plus, I don't think you guys have ever heard of Pascal's triangle. Have you ever heard of Pascal's triangle? Maybe some of you that did pre-calculus 30, you would have heard of Pascal's triangle at the very end of that course. But for others that haven't taken that class, you've probably never heard of Pascal's triangle. This triangle has a really kind of cool setup. How you create the numbers in this triangle is pretty neat, and it actually has a lot of applications for different things, especially for high-level math like binomial expansions. These are coefficients for the terms that you end up getting when you expand, let's say a plus b to the power of n. Okay, so these rows of Pascal's triangle are very clever. They actually connect with a larger binomial expansion. We're not going to get into that. But what this is trying to say is that these spots on this triangle, the way this is arranged, can be filled by these combinations. And this is part of also what we studied in pre-calculus 30. So 0 choose 0 is 1. So that goes in this spot right here. 1 choose 0 is 1, and that goes in this spot. See, you have a number here, comma, another number. That would be the second row. 1 choose 1, you'll find, is 1 as well. This third step here, this third number 3, represents the third row. So 1, 2, 3 numbers go in 1, 2, 3 spots. And you just kind of keep working down here. So this is asking you to kind of evaluate each of these and recognize some kind of pattern. So I'll help you through this. 2 choose 0 is 1. Choose 2 choose 1. Well, you can choose 1 two different ways from a group of 2. So that's 2. 2 choose 2. There's only one way you can look at 2 things and choose 2 of them at a time. One way. All right. 3 choose 0. 1. Oh, 3 choose 3 is also 1. There's a pattern you should be noticing. Just like in the fourth step, 4 choose 0 is 1. 4 choose, that's supposed to be a 4 there. 4 choose 4 is 1. Okay, so Pascal's triangle, you might notice here, the edges here of the triangle are all 1s. That's true. Okay, let's go back to this one. 3 choose 1. Who knows what 3 choose 1 is? That is, 3, because you could choose 1 three ways. What's 3 choose 2? These guys, and these guys out here. 3. Awesome. Okay. And finally, 4 choose 1 is 4. 4 choose 2? Anybody? It is 6, yes. What's 4 choose 3? It's 4. All right. So those are the values that go in Pascal's triangle. And did any of you, do any of you notice a pattern just looking at the triangle here now? Do any of you notice any kind of patterns in the rows or? Yes?
Well, going from the third row to the fourth, you add 1 and 2 to get 3.
Okay, going from the third row to the fourth, you add 1 and 2 to get 3. Yeah.
And then fourth row to fifth, you add 1 and 3 to get 4.
Okay, and this row to the last row, 1 plus 3 is 4. Yes, yes. If we were to continue on, that pattern would exactly continue. I would point this out as well, that 1 and 2 is 3, and 2 and 1 is also 3. Just like 1 and 3 is 4, look at this. 3 and 3 is 6, and 3 and 1 is 4. So, if you look at this, right, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3, and so on. So you add the numbers. Oh boy, my computer's crashing on me. But you add the two numbers to get the space that's right underneath it. And yes, we could start with a 1, like is our pattern. This next one, what would this next number be? This would be 5, choose 0 right here, and then 5, choose 1 would be what? 5. So 5 choose 2. Any guesses what 5 choose 2 might be? 10, yeah. And then 5 choose 3 is 10, and 5 choose 4 is 5, and 5 choose 5 is 1. That's exactly right. So that's how Pascal triangle is formed, and that's the connection with the combinations. Any questions about that? All right. Now, I'm going to give you guys a chance, a few more minutes to work on 17. I know you asked about it right away, but I'm pretty sure that not everyone has tried that yet. So I want everyone to try that. Go ahead, keep working on your assignment there for a few more minutes. Okay, let's take a look at 17. 17's a little bit of a tricky one to connect the combination formula, I would say, to this. First of all, this is what you want to recognize, that there are 0 diagonals here for a 3-sided. So n is 3 here. There are 2 diagonals for n equals 4. there are 5 diagonals for n equals 5, and there are 9 diagonals for n equals, I guess that's 6. 1, 2, 3, 4, 5, 6. Oh, still frozen, sorry. Okay, so we have diagonals and we have n here. The thing that we have to kind of figure out is r and how to get d from given n, okay? So when we make a diagonal, what has to happen is you have to draw a line from a vertex to a non-adjoining vertex. So there are no diagonals here because the 2 other vertices are joined by this point. So this is a diagonal here because it's connected to a vertex that's not one of these 2. So you have to stay away from the 2 that are right beside, but you can connect to any other ones. You have to stay away from the 2 that are beside a point, but you can connect to any of the other ones. So 2 seems to be some kind of special part of this. And so if you go like this, and this is the tricky part, like if you just kind of like test 2 being r, and you have n factorial, you have 2 being r here, and n minus 2 factorial. Okay, so that's kind of where you want to start. Now, at that point, how does the 2 factor in? Well, if we have sides are, let's say 3 choose 2. Okay, so what's 3 choose 2? What's that number? It's 3, right? Is it 3? Okay, so it's 3, but that's fine, but we need to have 0 diagonals. Okay, well, what's 4 choose 2? What's 4 choose 2? We just did that in the other question. 4 choose 2 would be, what, 6? Okay, come on now. Oh, thanks. 4 choose 2 is 6. 5 choose 2 is what? What's 5 choose 2? Do we have that in our? Awesome. Okay. 5 choose 2. 10, thank you.
Good.
Okay, so as we try and finish this question here, what we notice here is that if we do 3 choose 2, where 3 is n, that would be the number of sides, right? We get a value of 3. Now the number of diagonals is 0. 4 choose 2 is, that's n 4 sides. We get 4 choose 2 is 6, and the number of diagonals is 2. 5 choose 2 is 10, the number of diagonals here is 5. 6 choose 2 is 15, the number of diagonals is 9. So if we look at this further, this is the last thing that you want to notice. How do we go from 3 to 0? How do we go from 6 to 2, 10 to 5, and 15 to 9? Well, here we minus 3, here we minus 4, here we minus 5, and here we minus 6. So what that means is that you subtract the number, the n value, from the combination formula. So it's going to be n choose 2 minus n equals the diagonals, the number of diagonals. Okay? So that's what you're looking for number 17. Again, it's the number of sides, plug it in there. So if I had like 7 sides, right? It'd be 7 choose 2 minus 7 should be the number of diagonals that we would end up with. Okay, question?
Where do you get choose 2?
Well, again, so the question says, how can the combination formula be used to determine the number of diagonals? So I use the combination formula here, okay, right here. Now the two was the only kind of like, tricky thing, like where do you come up with 2? And again, in order to piece this together, one of the things that you can look at is that there are always 2 vertices that are connected to every point. There are 2 vertices that are connected to every other vertice. And those 2 almost are like, they're a common thread throughout there. The diagonals have to come to points other than the 2 that are immediately next to the vertex. So a diagonal can only be made with other points that are not of the important 2. So there's always that 2 that shows up. And again, you want to connect n with d. So n is going to be variable. D is going to be variable. R does not necessarily need to be variable. It can be a regular number. So again, just through different trial and error, you wouldn't land on 2 right away, but that's how you would figure that out. You would notice that if this 2 was a constant in this formula, then n could change, and it would change to deliver the appropriate d. If you put any other numbers in there, it wouldn't work. But yeah, so that's the stretch. This is a challenging question, right? But it asks you to, how do we determine the number of diagonals given the formula. So n has to change, right? D obviously has to change. R does not necessarily have to change. So that's the one we can look for a constant, and a reasonable constant might be 2, and you try that and you're good to go. All right, so that's a little bit of help with your homework there.